Historically viewed as a bastion of social interaction and craftsmanship, the hairdresser's profession is on the verge of a radical transformation driven by the convergence of artificial intelligence (AI), advanced robotic systems, and computer vision technologies. While the cultural narrative of hair care has long been built on human touch and conversation, available data and technological prototypes indicate that an ecosystem comprising high-torque direct-drive motors, millimeter-precision semantic segmentation, and autonomous decision-making systems is emerging to substitute human labor in this sector. This report reveals that the extinction of the hairdresser's profession is not a singular event, but a gradual process of value erosion, starting with the automation of administrative processes, moving to robotic assistance, and ultimately leading to full autonomous substitution. In light of data from medical robotics precedents, labor market projections, and current prototype analyses, this document delves into the inevitable trajectory toward algorithmic haircuts and the socioeconomic dynamics of this process. Historical context and the inevitability of automation. For centuries, a haircut has been a deeply human ritual where art, conversation, and trust intertwine. The client sits in the chair, engages in small talk, and relies on the stylist's tactile expertise to translate often vague instructions into a coherent aesthetic. This human connection, often cited as the strongest line of defense against automation, is being deconstructed by a new wave of technological capability. The premise that human connection is an impregnable fortress is challenged by shifting consumer preferences that prioritize speed, consistency, and convenience over social interaction. The narrative of automation in service industries typically follows a predictable curve: skepticism, followed by hybrid adoption, and finally ubiquity. The hairdresser's industry is currently in the late stages of skepticism and the early stages of hybrid adoption. Evidence from parallel sectors, such as cashierless grocery stores or the proliferation of robotic surgery, suggests that once the technical threshold for safety and efficacy is crossed, economic forces rapidly accelerate adoption. In this context, the extinction of the hairdresser is an economic inevitability born from comparing the inherent inefficiencies of human labor, fatigue, inconsistency, physical limitations, with the ruthless precision of robotic systems. Current prototypes developed by startups like Snips AI and engineers like Shane Whiten of The Stuff made here channel prove that the fundamental mechanics of a haircut, identifying hair, determining the cutting path, and executing the cut, are solvable engineering problems. While early iterations may appear bulky or slow, foundational technologies in computer vision and kinematics are advancing at a rate that outpaces human skill acquisition. The grooming landscape of the future will be defined not by the sound of scissors and gossip, but by the whir of servos and the silent processing power of cloud-based style algorithms. Technological foundations of the robotic hairdresser. Realizing an autonomous hairdresser requires the synthesis of three distinct technological pillars: advanced computer vision for mapping and segmentation, high-precision robotics for manipulation, and artificial intelligence for stylistic decision-making. Each of these technologies aims not just to mimic human capabilities, but to quantitatively exceed them. Computer vision and semantic segmentation. The primary challenge in robotic haircutting is the non-rigid nature of the workpiece, human head and hair. Unlike a metal block in a CNC machine, hair is fluid, dynamic, and chemically diverse. For a robot to cut hair effectively, it must first see it in varying degrees of detail, distinguishing individual strands from the scalp, ears, and background environment. Advancements in AI-powered computer vision have revolutionized hair segmentation. Technologies utilizing deep learning architectures like MobileNet and fully convolutional networks, FCN, have achieved an average segmentation accuracy of 89.9% across different genders and races. These models allow the robotic system to create a pixel-perfect mask of the hair, isolating it from the face and background. This segmentation is critical not only for executing the cut, but also for establishing safety protocols by creating no-go zones around sensitive areas like ears and eyes. Recent research indicates that the quality of feature extraction is more vital than the sheer size of the model. Specialized methods have demonstrated the ability to capture complex, curly hair boundaries that previously baffled sensors, outperforming general-purpose models by approximately 3 percentage points in F1 scores. This capability is further enhanced by vision transformer neural network models capable of predicting real-time segmentation masks for human subjects, classifying every pixel, including background, hair, body, face, and clothes, with high fidelity. While the human eye perceives hair as a mass, these systems see it as a processable topography of data points. The integration of depth cameras, such as Intel RealSense technology, allows these vision systems to move beyond 2D images into 3D topography. A robotic hairdresser does not just see a flat image of a head, it perceives a dynamic 3D mesh. This enables the system to calculate the curvature of the skull, cranial topography, and adjust the cutting angle in real time. Startups like Snips AI are effectively digitizing the consultation process by using this scan and analyze approach to determine the optimal cut based on head shape and hair type. In this process, a mapping occurs that leaves no room for human error. The robot knows every bump and dip on the head at a micron level. Robotic kinematics and end effectors. Once visual data is processed, it must be translated into physical action. The robotic arms used in these prototypes typically have 6-axis or 7-axis degrees of freedom, DoF, allowing for the complex articulation required to reach the back of the head or navigate around ears. However, a simple robot arm is not enough. The quality of movement is decisive. A critical advancement in this field is the shift to direct drive technology. Traditional electric motors typically produce high rotational speed but low torque, necessitating gearboxes to increase torque while reducing speed. Gears create mechanical backlash and reduce precision. Direct drive systems amplify torque without gears, improving the accuracy of both translational and rotational movements. This increases system stiffness, allowing the robot to execute complex, fade, cuts with minimal error and respond instantly to small head movements by the client, while human hand tremors or fatigue are non-factors. A direct drive robot can make microscopic corrections at speeds of 1/1000th of a second. The end effector, the tool at the end of the robot arm, has also evolved. Early experiments used standard scissors, which were mechanically complex to actuate and slow in practice. Modern iterations, such as BuzzBot-1 or vacuum-assisted systems reminiscent of the Floby, use modified clippers or suction-based cutters. The vacuum approach is particularly ingenious for automation. By sucking hair into a tube, it forces flexible strands into a rigid, known orientation, making the cut length mathematically predictable. This method simulates the tension a human hairdresser creates by pulling hair between fingers, but does so with much more consistent force. Robotics experts are also experimenting with multi-tool end effectors. Reach Robotics, known for subsea manipulation, produces modular arms with high power-to-weight ratios, demonstrating that compact, industrial-grade manipulators are commercially available. While their primary focus is offshore intervention, the underlying technology, high-dexterity manipulators capable of complex intervention, is directly transferable to the fine motor skills required for grooming. The precision required to inspect a subsea pipe is, provided sensor data is accurate, not unlike the precision needed to execute a zero-guard shave. Haptics and sensor fusion. Visual data alone is insufficient for a safe haircut. The human hairdresser relies heavily on tactile feedback, the resistance of the hair, the warmth of the scalp, the tension of the skin. To mimic this, robotic systems are integrating haptic feedback technology. These sensors allow remote or autonomous systems to perceive forces applied by cutting tools in real time. This force feedback loop is a critical safety layer. If the robot encounters unexpected resistance, e.g., a tangle or skin fold, force sensors trigger an immediate stop or adjustment. This concept, known as power and force limiting, PFL in collaborative robotics cobots, ensures the machine can operate safely in direct contact with a human. Standards like ISO 13482 for personal care robots explicitly govern these interactions, distinguishing them from traditional industrial robots operating behind safety fences. Furthermore, sensor fusion, combining data from LiDAR, stereo cameras, and capacitive skin sensors, creates a redundant safety net. Capacitive sensors can detect the proximity of human skin before contact is made, effectively giving the robot a sense of touch that extends millimeters beyond its physical surface. This multimodal perception allows the robot to navigate the unpredictable landscape of the human head with a level of safety that can statistically exceed human capability. The role of AI in style generation. The final piece of the technological puzzle is the brain of the operation. AI algorithms do not just control motors, they generate style. Generative AI, often powered by generative adversarial networks (GANs), allows the system to map various hairstyles to a client's specific facial features in a virtual environment before a single strand is cut. Smart mirrors, already in use in salons like the Amazon Salon in London, serve as the data collection interface for this intelligence. These devices allow clients to toggle between AR overlays of different hair colors and cuts. Every interaction with a smart mirror, every like, reject, or try on, feeds a massive data set on consumer preferences and facial geometries. Over time, the AI learns not just how to cut hair, but which haircut suits a specific face shape, likely better than a human stylist whose experience is limited to their own client history. This algorithmic styling capability is evidenced by systems analyzing over 190 hairstyles in real time and adapting them to individual textures. When coupled with robotic execution, AI creates a closed loop. The client selects a look from a digital catalog, or the AI suggests one based on biometric analysis, and the robot executes the code associated with that look. The hairdresser's artistry is thus encoded into repeatable, downloadable software updates. Medical robotics precedents, the ARTAS system. To understand the viability of the robotic hairdresser, one must look to the field of hair restoration, where automation has already established commercial dominance. The ARTAS robotic hair restoration system serves as primary evidence for the disruption of manual labor in hair procedures. The ARTAS system uses advanced digital imaging and precision robotics to harvest follicular units. It assesses the angle, depth, and density of each follicle in real time and uses a two-step sharp blunt punch technique to extract grafts without damaging surrounding tissue. The key takeaway here is scale and consistency. A human surgeon experiences fatigue. Hand tremors increase after hours of repetitive motion. The robot maintains sub-millimeter precision for thousands of extractions with no degradation in performance. Data indicates that robotic systems can achieve a hair graft detection accuracy of 97.4% for short hair. While some studies suggest skilled humans still outperform robots in yield rate, number of viable grafts harvested, the robot eliminates the variance of human error. The ARTAS system proves that robots can successfully navigate the biological variability of the scalp. Transitioning from harvesting, pulling hair out, to hairdressers, cutting hair to length, is not a fundamental reinvention of the robotic platform, but a matter of end-effector modification and software programming. Moreover, consumer acceptance of ARTAS demonstrates a willingness to trust robots for aesthetic outcomes. Patients often prefer the lack of linear scarring associated with manual techniques and the robotic precision. This psychological bridge of entrusting one's appearance to a machine in a medical setting paves the way for trusting a machine in a retail grooming setting. If people allow a robot to punch needles into their heads, they will allow it to approach with scissors. Current prototypes in the uncanny valley in grooming services. The automated haircutting landscape is currently populated by a mix of serious startups and maker experiments, each solving different aspects of the problem. Snips AI and the personalized fade. This California-based startup represents the high-end, software-first approach. By focusing on scanning the client's head to determine the optimal cut, they address the personalization argument often used by defenders of human hairdressers. Their system aims to perform the fade, a technically demanding cut requiring smooth transitions, using AI-driven clippers. This targets the most lucrative and repetitive segment of the male grooming market. Snips AI reduces the artistic part of hairdressers to a mathematical problem, promising a result that is custom to the client but robotic in precision. The Stuff Made Here robot. Shane Whiten's engineering project gained viral fame for its transparency regarding the challenges of robotic hairdressers. His system used a custom lever mechanism to rotate scissors around the head and a vacuum to manage hair orientation. While the results were described as interesting rather than salon quality, the project demonstrated the possibility of mathematically perfect haircuts, styles geometrically impossible for a human hand to execute, such as intricate lithophane patterns etched into hair. This introduces a new value proposition. Robots shouldn't just mimic human cuts. They should offer cuts humans cannot do. This implies hairdressers could evolve from a grooming service into an engineering spectacle. Panasonic's hair washing robot. On the maintenance side, Panasonic has spent years developing a 24-finger hair washing robot. Initially designed for elderly and patient care markets in Japan, this machine scans the head and applies the correct pressure for shampooing and rinsing. While not a cutter, it solves the wet work component of the hairdresser shop experience. The existence of this technology since the early 2010s highlights that mechanical capability for gentle, scalp-safe interaction is mature. The barrier has been cost and market positioning, not engineering feasibility. These robots mimic the dexterity of human hands while offering a standardized hygiene and massage experience. Reach Robotics Demo. Using industrial-grade manipulators, this demo showcased speed potential, completing a haircut in a time-lapse video in approximately 15 minutes. While reliance on manual length adjustment via attachments indicates full autonomous tool changing is a necessary next step, the fundamental motion control is validated. This shows robots can be not just precise, but fast. Despite these advancements, current prototypes still suffer from the uncanny valley of service. They lack the fluidity and adaptability of a human hairdresser. If a client sneezes, a human hairdresser instinctively pulls back. A robot relies on sensor latency. However, with the integration of direct drive motors and vision language action (VLA) models, this latency is decreasing to imperceptible levels. Dropping below human reaction times, these systems theoretically become safer than humans. The economics of displacement. The driving force behind the adoption of AI hairdressers will not be novelty, but economics. The traditional hairdresser shop model is labor-intensive and hard to scale. A shop's revenue is capped by the number of chairs and the number of hours a hairdresser can physically stand and cut. ROI of the robo-hairdresser. Collaborative robots, cobots, offer a compelling return on investment ROI for service industries. The cost of a cobot arm ranges from $15,000 to $60,000 depending on capabilities. In an industrial setting, ROI is often achieved in less than a year due to labor reduction and production increase. Applying this to a hairdresser shop, a human hairdresser works specific hours, requires breaks, gets sick, and takes a significant portion of revenue commission. A robotic kiosk can operate 24/7, requires no tips, and offers perfect consistency. For a shop owner, the robot's labor cost is electricity and a maintenance contract. Over a 5-year horizon, the robot becomes exponentially cheaper than a human employee. The kioskification of the industry. The likely deployment model for AI hairdressers is standalone kiosks. Concepts envision automated pods where a customer enters, gets their head scanned, selects a style, and receives a cut in minutes. This Uberization of haircuts decouples the service from the real estate and social overhead of a traditional shop. These kiosks could be placed in airports, train stations, or corporate lobbies, offering high-speed, low-cost grooming below the traditional market floor price. Labor market implications. Oxford's study on job automation assigned hairdressers a risk score of 0.8 on a 0-1 scale, classifying it as a high-risk profession. This statistical prediction is based on the reality that while hairdressers feels creative, a large percentage of the work, particularly men's cuts, is procedural and geometric. Fades, buzz cuts, and trims are repetitive tasks ripe for automation. The McKinsey Global Institute predicts that up to 40% of service jobs could be automated by 2030. For the hairdressers industry, this forecasts a bifurcation. Commodity haircuts, fast, cheap, standard, will be automated, while luxury haircuts, experiential, social, artistic, will become a niche, high-priced service. The mid-tier hairdresser providing a standard cut at a standard price faces the highest risk of extinction. Consumer psychology, trust and convenience. The primary counterargument to robot takeover is the hairdresser's role as a therapist. 85% of clients cite human interaction as a vital part of their experience. However, consumer sentiment is fluid. Surveys indicate that 65% of consumers are willing to receive a haircut from a robot if proven safe and effective. The shift in third-place dynamics. Oldenburg's concept of the third place, social surroundings separate from home and work, is critical to the hairdresser shop's identity. However, modern consumers increasingly transact in digital third places. The chat with the hairdresser is being replaced by scrolling on a phone during the cut. For younger generations, as the social value of physical interaction diminishes, the hairdresser's value proposition shifts entirely to the utility of the haircut. If a robot can provide a better cut in half the time, the social loss may be viewed as a net gain in personal time by the efficiency-driven consumer. Perception of safety. Trust is built on safety. Implementing speed and separation monitoring (SSM) and power and force limiting (PFL) is essential to winning consumer confidence. The medical industry has done the heavy lifting here. People trust robots to perform LASIK eye surgery and heart valve repair. Extending this trust to a haircut is a smaller psychological leap. Visualizing the cut via AR mirrors before it happens gives the client a sense of control often missing in a human consultation, further reducing anxiety. Roadmap to extinction, a phased transition. The extinction of the human hairdresser will not happen overnight. It will follow a phased roadmap of technological integration. Phase 1, the augmented stylist, present 2027. In this phase, AI does not cut, it consults. Smart mirrors and AR apps become standard in salons, using computer vision to analyze hair health and recommend products. Administrative AI takes over booking, inventory, and client management. The human hairdresser is still the execution engine. But the decision-making process is increasingly guided by algorithmic recommendations. Phase 2, Hybrid Workflow 2027-2032. Robots handle the grunt work. Automated washing stations, Panasonic style, and robotic roughing capabilities are introduced. A robot might shave the sides and back of a client's head with a perfect gradient, leaving the human hairdresser to scissor cut the top and style the front. This increases the human hairdresser's throughput, but de-skills the profession by reducing the skill requirement for fades. Phase 3. Autonomous Niche 2032-2038. Fully autonomous kiosks go live in high-traffic areas. These machines specialize in specific, lower-complexity cuts, buzz cuts, simple fades. They capture the convenience market. The traditional hairdresser shop begins to lose its maintenance client base, retaining only those seeking major style changes or luxury experiences. Phase 4. Algorithmic Standard 2040+. As robotics achieve human-level dexterity and AI masters complex styling, the robot hairdresser becomes the superior option for 90% of cuts. It can execute mathematically perfect geometry that a human cannot match. The human hairdresser becomes a rarity akin to a bespoke tailor, expensive, exclusive, and sought after for status rather than utility. Societal impact and the redefinition of grooming. The rise of the AI hairdresser will reshape the physical landscape of our cities. The interior design of grooming spaces will shift from the warm, wood-toned aesthetics of the past to a futuristic visual language, minimalist layouts designed for efficient traffic flow around robotic stations, accented by neon lighting and metallic surfaces. Hygiene, influenced by pandemics, will supersede social warmth, and a sterile, untouched shaving experience will become the new definition of luxury. Education in the sector will also transform. Vocational training for hairdressers will pivot from manual dexterity to robotic system oversight. The hairdresser of the future may hold a tablet monitoring the telemetry of 5 robotic arms rather than a pair of scissors. This represents a fundamental shift in the nature of labor, a transition from artisan to technician. Ultimately, the disruption brought by AI is the disruption of variability. It promises a world where a bad haircut is a statistical anomaly rather than a common annoyance. However, in scrubbing out error, we also scrub out the serendipitous nature of human connection. The robotic hairdresser is efficient, tireless, and precise, an embodiment of the industrial optimization of the self. As we surrender our scalps to the machine, we accept that looking good in the future will be more about engineering than art. Conclusion. The trajectory is clear. The technological barriers that once protected the hairdresser's profession, tactile feedback, irregular geometries, and stylistic judgment, are being dismantled by the convergence of advanced robotics and AI. While the transition will be tempered by the human desire for social connection, the economic efficiency and superior consistency of automated systems will inevitably erode the traditional market. The hairdresser of the future is a machine, and the hairdresser shop of the future is a style data center. The destruction of the old way is the construction of the new, a grooming industry defined by algorithmic perfection.